Swayam Prabha. Digital India. Educated India.
Hello all, welcome to Astrochemistry. This is lecture number 31. Now in the last lecture, I had introduced you to the problem of black body radiation and how Planck made an assumption. Planck made an assumption that only those frequencies of light would be emitted which corresponded to this equation, right? Which corresponded to this equation where h is some constant and nu is the frequency of light and n is a positive integer, okay, right? And is an integer. By integers, I'm talking about 1, 2, 3, 4, 5, etc., etc. Okay, the set of integers, set of positive integers greater than 1. Sorry, greater than 0. Okay, right? It's an integer greater than 0. 1 is also acceptable. So it should be n equals 1, 2, 3, etc., etc. So n is a set of all integers that are greater than 0. Okay, yeah. So only such values of frequencies are accepted. And using this idea, Planck made use of this idea to derive this expression, the steps which we skipped, okay, to get at E average is equal to h nu divided by e to the power h nu by kBt minus 1. Now, because of the nature of the exponential function, right? Because of the nature of the exponential function, your e to the power h nu by kBt minus 1, right, is always going to be much greater than h nu itself, right? In fact, this is greater than 1 itself, this exponential term for very large frequencies. And so the 1 can be ignored, and in any case, the h nu term, this is a linear dependency on nu, whereas this is an exponential dependency in the denominator. So therefore, your E average for very large frequencies, as is shown here, right, as is shown right here, correct, is going to be dropping off. So because the E average is much smaller, we were in the last class discussing, I had stopped the last class by telling you that Planck used this expression, and so therefore the average is going to be much smaller, and so we can conveniently ignore such larger frequency contribution to the theory curve. Okay, this is where we stopped. We shall elaborate upon it in this class. Okay, so now therefore for larger nus, okay, right, for larger frequencies, that is, because the denominator is much, the magnitude of the denominator is much larger than the numerator, right? Your E average is smaller, and E average smaller, E average being small implies, okay, right, implies that higher energy atomic oscillations, right? The higher energy atomic oscillations could be ignored. Now, what happens consequently? As the higher energy oscillations are ignored, right, and only certain frequencies are considered, instead of this curve going up, it reaches a maximum and it goes down. And this way, right, implies theory can match. I call it theory, but then this was theory, made out of desperation, you can call it, okay, right? Theory matched the experimental curve. Are we clear? So Planck solved a very important problem, that of, absolutely an absurd situation of like there being no light at all, no darkness at all, right? Because the frequency of light emitted is going on increasing, right? So he solved this absurd problem by making this rather drastic assumption that E equals nh nu, where n is a set of all integers. Now recall again, in the last class I used the phrase Planck proposed, Planck came up with. So I'll once again, use the same phrases. I used the phrases came up with right, or proposed. I never used the specific phrase derived, okay? So please note this point, right? Because Planck did not derive it. He proposed it. He came up with his idea and he did not know why. This is yet another important point, okay, right? He did not know why he was doing it, but because he had to, ensure that he matched the curve, he matched the theoretical curve with the experimental curve, he came up with this idea, all right? And then, of course, once you know that, okay, now you can ignore certain higher value of frequencies. So the curve will go down, and by fitting the curve, okay, right? By eventually fitting the theory curve and the experimental curve, Planck found out that the H value, okay, right? The H value is approximately 6 into 10 to the power. If I'm correct, it's 34. The unit is going to be joule seconds. Okay, right? Now, the modern value is slightly different. It is 6.6, not by 6.6. Okay, not by much in this part. Although including the exponent will make it significantly different. Okay, right? So Planck came up with the Planck constant as being approximately 6 into 10 to the power 4, and the modern value being 6.6 into 10 to the power 34 joule second, if I'm correct. Okay, right? 10 to the power minus 34. Oops, it's a small number, not a big number. Okay, right? It's a small number, 10 to the power minus 34, not plus 34. Please, I clarify. It's 6.6 into 10 to the power minus 34, not plus 34. Okay? All right. So, this is how, Planck explained it. Now, there remained a major conundrum. Okay, right? I'll now delete the graph because we no longer need it. In fact, we have retained the graph and then this equation from the previous lecture itself. Okay? E equals NH nu. The idea E equals NH nu, right? It was instrumental in solving the black body problem. Okay, where n is the set of all positive integers greater than 0. Okay, right? So now, but Planck really did not know the implication of it. He said, okay, well, I have to do it so as to, make this curve match this one. And by fitting the curves, the value of Planck constant was found to be something around 10 to the power minus 34 joule seconds. All right, this is where we are at. Now, this completely opened a new Pandora's box. This E equals NH nu expression. Now, people were wondering, what its interpretation could be. The larger question is that, okay, E equals NH nu is fine. It's a mathematical statement. But what is the physical implication of this mathematical statement? Okay, right? The idea is that only certain values, okay, right? Frequencies, right? Only certain values of frequencies, in other words, discrete values, right, are allowed, went against, okay, right? Went against the theory that light was actually a wave. Well, you see why it is, right? Because, if light were to be a wave, why should the light wave only be limited to certain frequency? Especially when we know that the electromagnetic spectrum, it spans a whole lot of frequency range, and there is no need for any particular frequency to not be disallowed, correct? So why is it that only certain values of frequencies are allowed? So this went against the notion that, well, light was a wave. Okay, but light did exhibit some properties such as interference in the Young's double slit experiments, and you can also diffract light, etc., etc. So based on all of these phenomena, light was thought to be a wave after all. The initial idea that light is a particle was rejected. So now, well, why should this light have only certain frequencies? And what is the physical interpretation? We had no idea. Okay, that is when, I'll delete this part. Einstein came along, and from among the several amazing things that he did, okay, Einstein via the photoelectric experiment, okay, right? photoelectric effect. Okay, we know the photoelectric. It's a single word, but I'm just using it here. Photoelectric effect. You know, Einstein, by explaining, okay. So this is explained. I'm just explaining it to you, the handwriting, EXPLAINED. Okay, Einstein explained photoelectric effect by an interpretation of this equation. By interpreting this equation, E equals NH nu. Now he said that, okay, E equals NH nu, right? Where N is, it can only have integral values. That's the key thing. Okay, that's the key thing to this interpretation, right? Etc. etc. You know, having like positive integral values meant light contained different particles. Now later on, you know, there was some other scientist by name Gilbert Newton Lewis, the guy of Lewis structures fame. Okay, right? He called these photons. Einstein did not call them photons, but you know, the idea that they are particles, okay, was already there. So light contained different particles, right? You know, if you have each of which corresponded to an energy of h nu. All right. So let's say, you know, if there are like 2 photons associated with light, the energy of light is going to be 2h nu. Now, because the number of photons is a very large number, you know, there are going to be lots of photons. So because the number of photons is going to be very large, right? You have lots of photons, and so the net energy is going to be, net energy of the light is going to be as many numbers of photons present times h nu. Are we good, right? So the interpretation of Max Planck's expression to solve the black body problem came about from Einstein, and he said that each of these n values, right? These n values corresponds to a number of. That's why, you know, it's a non-zero number. It's an integer. You know, the number of something, right? The number of particles. It's an integer. It cannot be, you know, 2.5, 2.8, 7.9, or an irrational number like pi e, etc., etc. Okay, it's an integral number, right? So that was attributed to a number of particles, right? Number of fundamental particles called as photons. The name photon came about much later. Okay, each of which corresponded to E equals h nu. The energy of each of which was h nu. All right. So this way, right? Now light was exhibited to actually, you know, like be a particle also. Now what is the consensus, right? In some experiments, okay, light does behave as wave. For example, in interference, exhibiting interference patterns, etc. Whereas in black body radiation, light, okay, right, behaves as a particle. Are we clear, right? So this is why, you know, this is where, following, you know, explanation of the black body effect and Einstein explanation, right, it was eventually understood, right? It is eventually understood, as we are today, that light, okay, right, light is both a particle and a wave. It's not simultaneously both a particle and a wave, okay. In some experiments, okay, right, in some experiments, the particle nature of light comes through. For example, in black body radiation, right, and in some other experiments, such as, for example, you know, your Young's double slit experiments, other experiments, right? Example, interference patterns. If it's too small, I've written interference patterns, okay, right? So in some cases where, you know, such as the black body radiation, its particle nature comes out. In some other cases, its wave nature comes out. So this gave rise to, you know, to a whole new branch of physics, which is actually responsible for our understanding of interaction of molecules with matter, okay, right? and how molecules in space could even be detected, right? So what did we see so far? You can in some sense think of the last few lectures as a small detour, okay, right? To understand about molecules in space, we first started looking at how does light interact with matter, right? For that, we need to understand the nature of light itself. And to understand the nature of light itself, I historically gave you a fact that, okay, light was understood to be particle by Newton in the 1600s approximately. And subsequent to that, light was understood to be a wave based on the various experiments that light satisfied. For example, performing interference, satisfactorily leading to interference patterns, etc. All right. Now, then came the big problem of black body radiation, and Planck used the idea E equals nh nu. Now, Einstein's interpretation of this equation as like the n term corresponding to the number of photons, okay, right? Number of photons overall led us to this massive interpretation that, hey, light is not just a particle or a wave, noting that how different, is the behavior of the wave and the particle, right? We in fact spent close to 15-20 minutes just elaborating upon the differences between a wave and a particle. These are completely different entities, right? But yet, the fascinating aspect is that light is both a particle and a wave. Are we fine with this? Okay. So, when we study the interaction of light with matter, right? As far as light is concerned, we have understood, although, there are several details that have been skipped, okay, right? But that's okay because, ultimately our interest is in astrochemistry in this course, with the idea that, our fundamentals should be clear and more details can always be learned in the other classes, okay, right? So light is both a particle and a wave. So the light part of light interaction with matter is complete. Let us now look into the matter part. What is matter? Well, anything that contains mass is matter, right? Yeah. So anything that contains mass is matter. And we're not talking about a macroscopic entity, okay? We're talking about matter as in atoms, molecules, etc., etc. We'll discuss that now, okay, in just a few minutes. Matter, especially at the microscopic level, because all these atoms and molecules, what are the dimensions of them? We are concerned with finding molecules in space. What are the dimensions of a molecule? For example, from your high school, the Bohr radius is of the order of 10 to the power minus 10 meters, right? It's roughly 0.53 angstroms, which is 0.53 times 10 to the power minus 10 meters, correct? We are talking about such very, such tiny substances, right? Extremely tiny substances. Now, when light passes through such tiny substances, we get signals, and that's how we are able to, detect molecules in space, all right? Now, such tiny substances, right? It turns out, right? It is not just light, okay, but matter. By matter, I'm talking about electrons, okay, right? Protons, atoms, and molecules. And of course, skipping through a whole lot of experiments which demonstrate this behavior, right? They are also surprisingly found to be wave particles. In other words, in some experiments, right, all these entities would behave as waves, and in some other experiments they would behave as particles. For example, in the photoelectric effect experiment, I'm not going to the details of photoelectric effect because it's part of several high school syllabi, right? We're talking about +1, +2 type. You talk about the light shining in and then like photoelectrons coming out, and you talk about the threshold frequency, and you say that the intensity of the light matters only beyond the threshold frequency, etc., etc. We don't need to worry about the details now, but based on experiments such as, in photoelectric effect, the electrons behave as particles. But, in another experiment called as electron diffraction, by exhibiting, interference patterns, electron behaves as waves. So therefore, right, in different experiments, right, both the matter, that is like at the microscopic level, electrons, protons, atoms, and molecules, they also behave as wave particles. In other words, we call this situation as like dual behavior, as duality. More specifically, we're talking about wave-particle duality. All right. So matter also, behaves just like light, and they exhibit what is called as wave-particle duality. All right. Now see, the key, we're not going into the details of what experiments led to matter behaving, matter exhibiting wave-particle duality. However, some key finer aspects have to be discussed. Okay. It is that you may ask me immediately, okay, right? Hey, when I say molecules, what about us human beings? Well, we're also composed of molecules, right? It is not inappropriate, right, from a scientific point of view, to call us as a bunch of molecules put together, a bunch of biomolecules put together, which eventually lead to the lipid layers, the membranes, the cells, right? And there is no part of our body which is not molecular in nature, right? Okay. So we can be thought of a bunch of molecules put together, right? So do we also exhibit wave-particle duality? It is a natural question to ask, right? Why did I stop with molecules? Why did I not say, biomolecules, etc., etc.? Why did I not do that? Well, there's a reason for it. The extent, okay, right? Once that you understand that both light is a wave particle as well as matter corresponding to wave-particle duality too, right? We now get the idea that the concept of duality exists. However, how to quantify duality? How to quantify wave particle? For example, how do you know until how big of a molecule is this wave particle idea valid? For example, I gave the example of a chalk piece, right? I gave the example of a chalk piece to illustrate the difference between particles and waves, correct? Now, I clearly called the chalk piece to be a particle. I did not call it a wave, right? And I said that, hey, the chalk piece, the number of particles is defined. One chalk piece cannot be atop another chalk piece, given that I've already said that one chalk piece occupies a given volume of space. I said all these things, right? Now, having said this, right, how do we quantify wave particle duality, and until when is it valid? Well, to answer that question, right, de Broglie again came up. There's this scientist called as de Broglie. He started his career as a historian, in fact, okay, right? And he in 1924 came up with a measure to quantify wave particle duality, right? Now, he came up with this idea, right, to quantify wave particle duality. We shall briefly see how he did this, okay? Now, using Planck's idea, you know that the energy of a photon is E equals h nu. Well, E equals nh nu, that corresponded to the energy of all the photons in the system, and E equals h nu is the the energy of one photon. Okay. Now E equals h nu, and this is from Planck. And you also know that your speed of light, okay, right? Your speed of light is nothing but the frequency, right, of the frequency of the light times its wavelength. This is nothing but like your this is in meters. This is, of course, in SI unit, I'll call it as joules. This is in meters, and this is the frequency, right? This is meters per second, correct? This is nothing but, in fact, speed equals distance by time. The same formula for particles in the wave mechanics lingo. That's it. Okay, right? So this is known from the wave theory. This was already known, right, from the theory of waves. Therefore, de Broglie suggested that your E equals hc by lambda. Are we good? Your E equals hc by lambda. Now, this is just by using these two equations, right? So your E equals hc by lambda. Now notice the dimension. Notice the dimension of this particular quantity here. What is it? Your E equals, right? Your energy is going to be joules, right? C is going to be meters per second. And H, right? H, from the previous discussion, E equals h nu. We saw that H corresponds to joule seconds, right? And your lambda is going to be what? Your lambda is meters, correct? If we consider, SI units. So the quantity h by lambda, right, it has dimensions of or units of joule seconds per meter. Now, what is a joule? You can think of a joule as like the easiest way, right? E equals half mv square. So that's going to be kilogram, okay, right, in SI units, meter square, right, kilogram meter square, s to the power minus 2, right, yeah. And the seconds is of course going to be s, and this is meter, which is effectively going to be kilogram, right, meter, this is plus 1 and minus 2, and this is per second. Are we good? So dimensionally, right, dimensionally, this corresponds to what physical quantity you can think of? Hey, kilogram, which is mass. And what is this? Meter per second is velocity, right? It's the magnitude of velocity. So what is this overall? This is nothing but momentum, some measure of momentum. I'll just write it as P. All right? I'm going to be writing it as P here. Are we good? Do you understand, how, dimensionally, right, this h by lambda actually, kind of corresponds to a momentum. Okay. It also turns out, that I'm not going to give you the details, okay, from the theory of, in other words, okay, right. So in other words, right, now this expression, this E equals hc by lambda, right, E equals h by lambda times c, right, can also therefore be written as E equals pc, where p is some momentum. All right, so this is some momentum. Okay, right? So your E equals pc. Now, but what momentum are we talking about? This is for light, right? We obtain this for light, and this is also true for the electrons, atoms, molecules, etc. Whenever you have like wave particle duality, this is going to be valid. Valid for wave particles. Now this is going to be valid for waves, right? For all waves, which means for also wave particles. This equation is also going to be valid for wave particles. And so therefore, you can now associate, okay, right? You can now associate any wave particle with a momentum also. Are we clear? See, in fact, starting from the Maxwell equations, okay, right? Starting from the Maxwell equations, the same E equals pc can be obtained, okay, starting from Maxwell's equations. We're talking about like electrodynamics, okay, classical electrodynamics, but we're not going into that specific detail, okay? We don't worry about, if the last phrase I said, oh, suddenly I was able to understand everything, but suddenly, you threw me off by using this phrase starting from Maxwell's equations. Don't worry about it. I'm just telling you that this particular expression, E equals pc, can also be obtained from a bit more rigorously, instead of using dimensional analysis, okay, using this idea is called as Maxwell's equations. If you do not know about them, perfectly fine. We do not care about it for our course. Okay, right? Please note that. Okay, so we now have, for the wave particles, some magnitude of energy associated with the frequency, right? And also with the momentum, correct? And this h by lambda corresponded to a momentum term. Now, so what we obtained was that for wave particles, okay, right, h by lambda is equal to p. All right, this is what de Broglie suggested. So I stop right here, and we shall continue from exactly this point in the next lecture. Thank you so much.